Good day, students. I am Dr. Monica Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. Today I am going to deliver a lecture of MSc Previous Physics. I am dealing with first paper, which is Classical Mechanics. In my previous lectures, I have taught you about Lagrangian equation, and for that we have derived principle of virtual work. This is the principle of virtual work, summation Fi dot delta Ri equal to 0. And using this principle of virtual work, we have derived D'Alembert principle. This D'Alembert principle is summation over all the particles Fi minus Pi naught, which is termed as reversed effect force, dot delta Ri equal to 0. And using these principles, we have derived our general form of Lagrangian expression. The general form of Lagrangian expression is derivative with respect to time d del t upon del qj dot minus del t upon del qj, this equal to capital Qj. Here capital T is the kinetic energy of n particle system. Small qj being the generalized coordinate, and qj dot is the derivative of qj with respect to t. And capital Qj, this is the generalized force of the n particle system. In this Lagrangian expression, here we have chosen coordinates Qj. These generalized coordinates are independent coordinates. So depending upon the number of generalized coordinates, we will have the same number of Lagrangian equations. This general form of Lagrangian expression has been modified for conservative system as d by dt del L upon del Qj dot minus del L by del Qj equal to 0. Here, what is L? L is the Lagrangian of the system, and it is equal to kinetic energy minus potential energy. So if we have to determine the Lagrangian of the system, we must know its kinetic and potential energy. In my previous lecture, I have given you students an assignment. Today, I am sharing with you the answers of this assignment. The first question was, generalized coordinates are. What I have just now told you that these are the coordinates which are independent coordinates. So the correct option among these four is the B option, that is they are independent coordinates. Now the second problem was of rigid body. Constraints in rigid body, they are whether holonomic, non-holonomic or scleronomic or none of these options. As I have told in my earlier lectures that holonomic constraints are those constraints which are expressed by a particular fashion of equation, that is functional dependence of coordinates and time equal to 0. And in a rigid body, we know that the distance between the particle will be fixed. That is, if we assume that there are two particles, I and J, and the distance between them is Ri minus Rj, then we can write Ri minus Rj equal to C. So we have function of coordinates to be equal to 0. And these constraints are termed as holonomic. So in a rigid body, we will have holonomic constraint. So students, for the second question, the option will be A. Now in a third problem, we are having a particle which is moving on the arc of a circle. And the suitable generalized coordinates for the system will be, since we are having a particle which is moving on circle, the generalized coordinates will be, as the problem is in r theta coordinates, But since the circle radius is fixed, that means r will be fixed. What is the variable here? Theta is only variable here. So for this problem, the generalized coordinate will be theta only. So solution of the problem third is B, that is theta only. Now moving over to the fourth problem. What is the fourth problem was a rigid body moving freely in space has degree of freedom. Since we are having a free particle, so it can move in any Cartesian coordinate direction. That means whether it can be X, Y, or Z. That means it will have a degree of freedom 3. So the correct option for the fourth question will be A, that is 3. So this was the assignment which I have given you in my previous lecture. Now we will discuss the problems related to the Lagrangian equation. We have already derived the Lagrangian equation of motion. The Lagrangian equation of motion is d by dt del L upon del Qj dot minus del L upon del Qj equal to 0. What we have to find here, we have to find the Lagrangian equation of motion of linear harmonic oscillator. For linear harmonic oscillator, since we are given that harmonic oscillator is linear, that means we are having only one dimensional system. So here I am taking only x direction. This is a spring of spring constant K and a mass M is attached to it. This is our system of linear harmonic oscillator. Now to solve this expression, I must know my L, that means I must know the kinetic and potential energy of the system. And we must also know our generalized coordinate. Here, since I have told that it is a linear harmonic oscillator and I am choosing only x direction, so generalized coordinate will be only 1 and it will be x. Now what about the kinetic energy? Kinetic energy, as we know, it is half mv square. And v is the velocity of the particle. It will be in the x direction and it can be expressed as x naught. So kinetic energy will be half m x dot square. And for an oscillator, the potential energy is half k x square. So knowing the kinetic and potential energy, we can easily find out the Lagrangian of the system. L will be, here it is shown, half m x naught square minus half kx square. Now L is known to us, generalized coordinate is fixed, that is equal to x. So we have to simply solve this second order differential expression. What is del L by del x dot? Differentiating this L with respect to x dot, I get it to be equal to mx naught. Now, what is the second term of the expression? Second term is del L by del x. Differentiating L with respect to x, I get minus kx. So putting these value, collecting all these value, I got the expression mx double dot plus kx is equal to 0. So from here, we can easily write it x double dot plus k by m x equal to 0. We know that this is the expression of simple harmonic motion, which is having an angular frequency omega to be equal to under root k by m. So we can simplify Lagrangian equation of motion if we know the kinetic energy of the system, potential energy of the system, because L is simply kinetic minus potential energy. And we have to choose our generalized coordinate. Here I have shown that in this problem, we are having only one generalized coordinate, that is equal to x. Now I am going to discuss another problem. This is the problem of simple pendulum. What is a simple pendulum? We know that simple pendulum is simply a thread, or we can say a string, at the end of which a bob is attached. Here I am showing this by OA. This is the point of suspension O, and this is the bob. This string is inextensible string, and so the length of the string will be fixed. Here I am taking the length of the string to be small l. Now I am displacing my bob from its mean position. Its mean position is denoted by A. It will oscillate about its mean position. This will be a simple harmonic motion. Now I am taking at any instant, let theta be the angle between its rest position, which was denoted by OA, and its deflected position I am taking as OB. Now the angle between rest and deflected position at this instant is theta. L is fixed, variable is theta, so we have only one generalized coordinates, that is theta. Assuming the mass of this bob to be small m, I'm writing the kinetic energy of the system. Kinetic energy is half mv square, because here the motion is rotational. So I am changing my v to omega. That means I am taking linear velocity to angular velocity, since v is equal to omega r, and omega is simply theta naught. So I am writing v to be theta dot omega r. What will be the radius here? Radius formed by the circular motion will be measured from point of suspension O, which is fixed, and this radius will be equal to L. So omega r means in my problem L theta naught. Substituting value of V, I got kinetic energy of the system half ml square theta dot square. Now I have to solve my Lagrangian equation of motion. I find my kinetic energy. Another unknown factor is potential energy. Now I am going to determine the potential energy of the system. As we know, potential energy is mgh. What is h here? I am showing this by my figure, that in my deflected position, the particle is at point B, and at mean position, it is at point A. So from B to A, in moving from this point to this point, bob has fallen freely through a vertical distance, which is CA. So here the height is CA. MGH means MGCA. Now I have to find the distance CA. From this figure, we know that CA is OA minus OC. What is OA here? OA is the length of string. So substituting in spite of OA to be L, and in spite of OC, I am putting it as L cos theta. I'm taking the component of L across this direction. It is L cos theta. So potential energy will be mgl 1 minus cos theta. Kinetic known to me, potential known to me. I am finding Lagrangian. L is T minus V, half m L square theta dot square minus mgl 1 minus cos theta. So in order to solve the equation of motion, I find my Lagrangian. Now the generalized coordinate here is theta. Only one coordinate is generalized, and that is theta, as L is fixed. So the Lagrangian equation, in spite of generalized coordinate, I have chosen theta, d by dt del L by del theta dot minus del L by del theta equal to 0. Differentiating the Lagrangian of the system with respect to theta dot, here differentiating it with respect to theta dot, I have only first term which is having theta dot. Differentiating simply with theta dot, I will get ml square theta naught. Now, in the second term, I have to differentiate it with respect to theta. In Lagrangian, I have one term of theta, that is plus mgl cos theta. So on its differential, I get the constant term as it is, which is mgl, and differential of cos theta is minus sin theta. So solving this expression, because here I am having again differential, m is constant, which is the mass of Bob, length is constant. So I will differentiate only theta dot. I will get ml square theta double dot plus mgl sine theta equal to 0. Rewriting this expression as theta double dot plus g by l sine theta equal to 0. I am having simple harmonic motion, and I am taking the amplitude of the motion to be very small. So when the motion is small, that means I can simply write sine theta to be approximately equal to theta. So here I am rewriting sine theta as theta. So the expression becomes theta double dot plus g by l theta equal to 0. This is the equation of motion of simple pendulum. And from this expression, we can also find out the time period of simple pendulum. Since omega, from here this is equal to omega square is equal to g by l. So I can find out my time period. Time period is 2 pi upon omega. So time period of the simple harmonic motion will be 2 pi under root L by G. These were the problems of Lagrangian equation of motion. I hope students, you must solve such type of more problems. Thank you students for watching.